Okay, so this is activity worksheet 13-3, interpreting SPSS output for correlation and regression analysis, and also how to report those results in the APA format. So that's what the worksheet looks like, and let's see. So a couple of questions, and once you know how to read and interpret SPSS output for correlation matrix, it's pretty straightforward to answer these questions. Which variable is significant correlated with the height? Explain the correlation. What is significant? What is the size? What is the direction? And also explains the results of regression analysis predicting height using life satisfaction as the predictor. Okay, so these are the basic questions, and I want you to take a look at those questions and familiarize yourself with what are the questions that you need to answer, and then come back. You can pause the video if you want, and then after you look over the questions, come back and we can look at the output. Okay, so if you, in SPSS, if you ask SPSS to just run a bunch of correlations with a couple of different variables, so here's the example. This is based on 62 students, surveys, Psych 9 students I surveyed, not this year, but the last time I taught Psych 9. So I had 62 students in total, and I measured their heights, self-report, how many units they take, GPA, number of siblings, their life satisfaction on a scale of 1 to 5, what is the level of life satisfaction, and finally, gender. Now, you may be a little curious why how can gender be used in correlation? Didn't we say that for correlation and regression analysis, the variables have to be numerical? So yes, the variables have to be numerical, except one scenario, except one special case. Which is if you have a categorical variable with only 2 levels. Okay, if you have 3 levels, you cannot do that. So with gender, if you only consider male, female, 2 categories, and you can code those 2 categories, usually just do like 1, 2, or 2, 1, 1, 0, 0, 1. Doesn't really matter what number you use, but most likely people use those numbers 1 or 0. And it's called dummy coding. It's not a real value, but you assign a value to represent a category. And that categorical variable only has 2 levels. So this gender in this case is a dummy coded, we call that a dummy coding, D-U-M-M-Y, dummy coded. Okay, if it's a dummy coded categorical variable with only 2 categories, then yes, you can use that in the regression analysis and correlation analysis. So when you provide these 1, 2, 3, 4, 5, 6 variables, what SPSS produce is a 6 by 6. We call this a correlation matrix. It's a matrix. It's an array of correlations. And you find the correlation at the intersection of 2 variables. So for example, what is this number 1? This is the correlation between height in inches and another variable, which happens to be also height in inches. So in other words, this is a correlation between variable height in inches with itself. And of course, correlation is 1. Correlation between the number of units and the correlation between the number of units, 1. Okay, so in this correlation matrix, all the numbers, you have 6 numbers on the diagonal that all equals 1, because this is these are the correlation of variables with itself. Now, what is, let's say, which variables are correlated with, let's say, life satisfaction? Okay, so that's 1, life satisfaction. Now, height in inches has a correlation of 0.322 with life satisfaction. And number of units? No. Number of GPA? No. Number of siblings, no. And finally, gender, negative 0.197, p-value equals 0.125, so it's not significant. So it turns out that the only significant predictor, only variable of the 6 that we calculated, the only variable that has a significant correlation with life satisfaction is height in inches. Okay, so you look for the intersection, and this is the correlation. So for example, what is the correlation between GPA and the number of units that they take? So GPA and number of units that they take. So equals negative 0.026. So the correlation is negative 0.2026, which is not that different from 0. So we know it's not going to be statistically significant. All right, so this is how you interpret the correlations in this correlation matrix. And we can take a closer look at this particular correlation, which is between, if you remember from last slides, it's from between satisfaction and height, how tall you are. So the correlation equals, if we use the APA format, lowercase r, italicized in parentheses, degree of freedom, right? So n equals 62, and so we have degree of freedom for correlation equals n minus 2. So 62 minus 2 equals 60. So with 60 degree of freedom, correlation coefficient equals 0.32. We round to 2 decimal points. And p equals significance two-tailed, 0.01. Okay, so this is how we would report the results of a correlation in APA style. Now, you can interpret this correlation. Right? One of the worksheet activity is to answer the question, what is the relationship between life satisfaction and height? So you can figure that out. Number 1 is significant. Number 2, consider the size, 0.32. Is it large, medium, small? And you can also think in terms of whether the correlation is positive or negative. And based on that this is a positive correlation, you can provide a proper explanation of this correlation. So basically you would say something like people who are taller, on average, they tend to have, you can fill in the rest. Okay, so that's the interpretation of correlation coefficients, which is pretty straightforward. Next, let's take a look at regression analysis. Now, this is what the regression analysis from SPSS look like. So you have a couple of tables, the title regression, and you have a table called variables entered, removed. It tells you what is the independent variable entered. So this is the independent variable, height in inches. And it also tells you the dependent variable, which is what you try to predict, that is life satisfaction. So in terms of xy, this is the y, and height in inches is x. Right, so this table essentially tells you which variable is the IV and which is the DV for the regression analysis. There you have when you conduct a regression analysis, you always have an ANOVA table, which tells you the significance of the regression equation, or sometimes we use the term the regression model. Okay, so in this, this is what the ANOVA tells you. This is the significance of the regression model. And we also have another part. It's called a model summary, and here we can find R squared. Right, find R squared. This is the measurement of effect size. It tells us how much the model, the regression equation, can predict. Okay, so R squared. And finally, we have a table that gives us the coefficients. Okay, so let's take a closer look at each one of these tables. We'll start from the analysis of variance table. And so when we interpret SPSS output for regression, we basically try to find the information, try to find the answer to these three questions. Question number one, is a regression equation or model statistically significant? And then that question, answer to that question is to be found in the ANOVA table. So we, just like any analysis of variance, we look for the F statistic and the P value. So anything that's less than 0.05 is considered statistically significant. So in this case, P equals 0.01. Then obviously we have a statistically significant regression model. And we have degree of freedom. When you report the F value, you need the 2 degrees of freedoms. So degree of freedom for regression equals 1. You have 1 predictor. Actually, you have 2. You have the constant, which also counts as 1. And you have a real predictor, which is the independent variable. In this case, it's height. So the constant plus height, you have 2. 2 minus 1, 1. That's why you have 1 degree of freedom for regression. And it just also happens that the degree of freedom for regression also equals the number of independent variables that you have. And this is error, this is residual, this is total. Okay, so yeah, we have n equals 62. So the total degree of freedom is n minus 1, 62 minus 1 equals 61. Minus regression, this is the degree of freedom for error. So when you report this statistics, you would say the regression equation was statistically significant. F is italicized. 1, that's 1 error residual, right? 60 equals 6.95. P equals 0.01, meaning the regression equation taken as a whole, it is statistically significant. Now, if the regression equation is significant, next question is effect size. Okay, we can make prediction. Next question, how much can we predict? How much can we predict is effect size. And for regression analysis, the effect size is R squared. It tells us the proportion of a variance in the dependent variable can be explained, can be predicted based on the independent or the predictor variable. Okay, so in this case, it's 10.4%. And the regression model predicted 10% of the variation in grade. R squared equals 0.104. Now, one thing you can verify, of course, is that you remember the correlation between height and life satisfaction equals 0.322. So what is square of 0.322? Well, 0.104. Okay, so this is how much we can predict. So again, question number 1, do we have a significant regression model? If it's yes, then next question, how much we can predict. Third question, what are the regression coefficients? In other words, you ask the question, what is the regression equation? So regression equation, remember, is y prime equals a plus bx. So what is the value of a? What is the value of b? And for that equation, so those numbers, we can get the numbers from under unstandardized coefficients, b. Okay, so that is our regression coefficients. Constant is a. And coefficient for height in inches is the regression coefficient or the slope b. Okay, so the regression equation is y prime, the predicted value of life satisfaction equals negative 1.23 plus 0.07 times x. Standard error provides a measurement of how accurate these point estimate really is. Okay, so when you write the regression equation, we don't really need these numbers. So that's the unstandardized coefficients. So this is the equation we would use if everything just stick with the raw scores. Now, we also have something interesting here. This part is called the standardized coefficients, beta. Instead of b, we use beta. So what is beta? Beta, essentially, this is the regression coefficient if both x variable and y variable are expressed in standardized z-scores. So we can write an equation that's based on z-scores, right? So we can say, okay, here's a z-score of y and its prediction. Okay, so zy prime equals. Now on this side, we also need a z-score, right? So this is also z-score, and this is z-score of x. So this is a predictive variable. Now what is the regression coefficient here? This is where the beta coefficient comes in. It's 0.32, which you probably recognize in this case. If you're running a simple regression analysis, it happens to be the correlation coefficient. If it's a multiple regression analysis, then you can still write such an equation, but the beta coefficient is no longer going to be correlation. So this is correlation only because this is a simple linear regression. We have only one regression equation. So the regression equation can also be written in the z-score formula. Standardized coefficients, beta, is for standardized z-scores, z-score formula. Now, if we stick with the z-score formula, there is no constant, or the constant always equals 0. So we don't need the constant. And we really don't need this part if we are conducting a simple linear equation, because this is going to be redundant. The level of significance is the same as the significance of the overall model, because this model includes only one predictive variable. Now, if it's a multiple regression analysis, then it's a different story, because you can have a significance of the overall model, and you can look at the significance of each individual predictor. The significance of the predictor is provided by t-test, and this is where you find the level of significance, 0.01. So height in inches is a significant predictor of life satisfaction. Okay, so not only the entire regression equation is significant, height in inches is also a significant predictor of that relationship. So that's the interpretation of SPSS output for correlation and for regression analysis. Right? So again, we have quite a bit of a part of this regression output. So you start with ANOVA, which tells you the significance of the model. Next, if this is significant, then you move on to the next part, which is effect size, how much does the model predict. Then you move on to the part that's coefficient, and use these numbers that you can write the regression equation. Now, what happens if you look at the ANOVA and this is not significant? If the p-value is greater than 0.05, then what you do? Well, that's easy. You just say, the regression equation was not significant. Here's the p-value, here's the f-value, here's the p-value, and then end of a story. So if the regression is not significant, there's no need to think about the r-squared or the coefficients, because the regression equation is not significant. Okay, so that's SPSS output. And let's talk just a little bit about how to report the results. This is kind of consists of the same formula we used for any analysis. Number one, you describe the analysis. Number two, you describe the statistics. And number three, you explain what the results mean. And if you need a table, provide a table. Okay, so we'll start from correlation. Correlation, if you have only one correlation or two, or maybe even three, then it is totally entirely okay to just describe the correlation in the text. But if you have a lot of correlations to report, such as in this case, we have 6 by 6, we have quite a few correlations. Of course, half of that correlation matrix is redundant, but still we have a lot of correlations. In that case, we can highlight, we can describe the correlation that's important in the text, but we don't need, there's no need to repeat everything. Okay, you can just refer the participants to the table for descriptions of statistics, for descriptive statistics, and the correlation coefficients. Okay, so if we analyze the language here to find out which variables hide these variables, what are the relationships, and remember gender is a dummy-coded categorical variable with 2 categories. It's a dichotomous variable, so you need to indicate how the variable was correlated or was coded, because if you code male equals 1, female equals 2, the correlation is going to come out in a certain direction. But if you code, for example, female equals male equals 2, female equals 1, then the correlation would come out in the opposite direction. Okay, so you need to provide that information so people can, if you have a significant correlation that involves gender, you can interpret that correlation properly. Next, results show that the height was significantly correlated with life satisfaction are degree of freedom, correlation, p-value. Next sentence explains that correlation, indicating that taller individuals tended to report higher levels of life satisfaction, right? So the 2 variables, height and life satisfaction, they change in the same direction. In addition, height was significantly correlated with gender, R equals negative 0.65, P less than 0.001. Okay, so how do we interpret this negative correlation with gender? Well, think about it. Height, when height goes up, when height increases, what happens to the variable y? It's a negative. It goes down, right? So high number means female, lower number means male. So in other words, taller people are more likely to be male, which happens to have the lower value on gender variable, right? So the variables change in the opposite direction. So indicating male individuals tend to be taller than female individuals. No other correlations were statistically significant. See Table 1 for the description of statistics, descriptive statistics, and correlations. Okay, so this is a table that we describe all these correlations. Now, there's no need to describe this 1, 1, 1, 1 because that's redundant. And we only need to display to report half of the correlation matrix because the other half is redundant. The correlation between height and units is the same as the correlation between units and height. It does not change the correlation. So there's no need to repeat the information. And so this is the kind of basic APA format. Table number is italicized, is in bold font size. The title of the table is italicized. And you can report the sample size here. And this is just a little trick to save some space to make the table look better. So we have a bit of space here, so you can say 1 means height, 2 course units, 3 GPA, 4 sibling, 5 life satisfaction, and etc. So for the column heading, instead of height, course units, because we don't have enough space here for course units. So instead of saying these, we are just saying 1, 2, 3, 4, 5, 6. So 1 is height, 2 is course units, 3 is GPA, and etc. Okay, so this is just a way to make the save some space and make the table look better. This is a note that life satisfaction was rated a 5-point scale. 1 equals very unsatisfied, 5 is very satisfied, and gender was coded as male equals 1, female equals 2. This information is necessary because It's relevant to how we interpret the correlations. And finally, the last point I want to mention in this table is that by convention, we use asterisks to indicate the level of significance. If a correlation is significant at the 0.05 level, meaning if a p-value is greater than 0.01 but less than 0.05, we use one asterisk. So if you see one asterisk, it means p is less than 0.05. Now, 3 asterisks means p is less than 0.001. Now, we don't have anything here that shows that something that's significant, p-value at 0.01 level. So we don't have that. But if we did, then we would say 2 stars means p less than 0.01. Okay, and then we would put it over here. So if we have a correlation that's significant at the 0.01 level, but here we don't, so we don't really need this. And another thing I want to mention is that this is sort of the conventions. The 1 star means significant, less than 0.05. 2 stars means significant, 0.01. 3 stars, it means significant, 0.001. Okay, so that's convention. Now, this is not the convention that SPSS observes. So SPSS does not use this convention. And so you need to be careful when you transfer the numbers, correlations into your writing, and you have to take a look at the table and say, look, oh, here is the p-value, how many stars I should use. So don't just copy the stars from SPSS, the tables in SPSS. SPSS at most gave you 2 stars. So even if p is less than 0.001, you still get only 2 stars, but you should use 3 by convention. Okay, so that's correlation. What about the regression analysis? So this is the part of our regression analysis. And again, you start with a description of the analysis. So a linear regression analysis was conducted to predict life satisfaction. This is dependent using height as the predictive variable. So here's the order. Regression equation was significant. This is f value, p value. Next, because it is significant, effect size. So it predicted 10.4% of the variance in life satisfaction. See table 2. So you can, if you want to provide, you can add the regression equation here and say the regression equation is y prime equals whatever number plus whatever number times x. Or you can just say, go see the table, go look at the table. So table 2 is a table for regression analysis. So the information that you obtain we put in this table come from the SPSS output. So we still have the r squared equals 0.10. We have the f statistic for the entire regression equation, and this is a p-value for the regression equation, right? And then we also have variables, meaning this is the independent variable predictor, which is height. And here we have a b, that is unstandardized coefficient b. Okay, so this is where the information come from. So this is height. No, this is b. No, sorry. This is constant. Let me discard and try again. Okay, so this is unstandardized coefficients, right? We have unstandardized coefficients, b. So this is b. And what is the coefficient for height? So for height in inches, b equals 0.07. So 0.07. Next column, you have standard error of B. So this is SE standard error B, italicized, and that is 0.03, right? This is 0.03, so that's 0.03. And finally, you report the standardized beta coefficient, so that is beta. By convention, Greek letters are not italicized, so you have beta and you have 0.32. Now I decided to use 1 asterisk because technically this is slightly higher than 0.01. If it's less than 0.01, then we would have used 2 stars, 2 asterisks. But this is 0.011. So strictly speaking, it's greater than 0.01 but less than 0.05. So in this case, we would just say 1 star, it means P equals 0.01. So this is the table for regression analysis would look like. By convention, we don't always include the constant, but if you want, you can always include the constant. You would just say constant B negative 1.23 and SEB 1.74. Of course, you don't have beta. Now, what if it's a multiple regression analysis and you present such a similar table? Well, the table would look very similar. You still have R square, still have F value, still have a P value, but then you have height as a first predictive variable, x1, and then you have something else, x2, right? Something else. You also have B, standard error of B, and beta, and etc. Okay, so this is how you would we would report the results of a regression analysis. Again, here's the write-up. As you can use this example to finish your writing. Don't copy in verbatim. I don't think that's a good idea, but understand what you try to report and just kind of in your own words type up 1 or 2 paragraphs and then make a table for correlation and also make another table for regression analysis. Now, if you have a question about how to create a table, APA style table in Microsoft Word, if you don't know how to do that, well, that's easy. Go to YouTube. Go to YouTube and just search how to create APA format, APA style table in Word. And you can find quite a few videos of varying quality, and find one that's with good quality and just follow the instructions, follow the examples in the video. Okay, so again, there's a lot of good information on YouTube. You just need to know where to find them. So this is the end of the activity 13-3 and also the end of this video.